everyone. Let's do a simple exercise on Argus Lab today. I have already written the aim of the exercise we are going to do today and how to tabulate it. So the aim is compare the bond lengths of methane and ethane molecules using quantum mechanical method. I will tell you in some other lecture what are quantum mechanical methods and what are methods. So here we are using quantum mechanical methods. Observation calculations, you have to draw a table where I have already mentioned the molecules methane, ethane. Their optimized geometries will be pasted here. So when the results are tabulated properly, it is easier to analyze the results. And CC bond lengths and CH bond length, heat of formation. Here is the Argus Lab window. Open a new file and draw a methane molecule. So I will simply right click. Here is the carbon, add hydrogen. So this is a methane molecule which is in sp3 hybridization. You can see here in geometry they have mentioned carbon. Here carbon is selected in tetrahedral form, which is sp3 hybridization. So when you add hydrogens, it will automatically complete the valency and add 4 hydrogens to it, right? If you want to delete hydrogen atoms, you can simply click on this, then hydrogen atoms will be gone. But we need it here. I will again click on this. So here is the methane molecule. If you want to label the names and symbols of the atoms, here it is C1, H2, H3, H4, H5. Right? Now if I find the geometry is not proper, I must clean it. Here is the clean geometry. So cleaning the geometry means we have done in last class how to and where to save the output files. I have created a separate folder on the desktop. So here my all output files will be saved. If I am cleaning the geometry, system is doing some calculations and showing here geometry optimization converged. So it is again optimizing the structure using molecular mechanics method, which is I will tell you in detail what is and what is QM later on. Now we need to do the calculations using optimized geometry, second option. AM1 method. This is a quantum mechanical method. When we cleaned the geometry, method by default was selected, which is universal force field. I am selecting AM1 or Steen model 1. You can select PM3, MNDO, any of these. These all methods are semi-empirical methods. So Argus Lab works with only semi-empirical methods. And we start. Here again, it took only fraction of seconds to converge the geometry. Geometry optimization converged. If the geometry is not converged, we are supposed to make some changes in settings before doing calculations. We will see it later. So here is the structure of methane with all optimized geometries. All optimized bond lengths, bond angles, everything. So now we need to see the bond length. What is the bond length? Here is only one kind of bond, CH bond. For that, you are supposed to select the atoms between which you want to see the bond length. Click on hydrogen, press Ctrl on your keyboard and then carbon. Sorry. This is selected and carbon is selected. Now go to monitor and distance. See, only the distance option is highlighted because I have selected 2 atoms and between 2 atoms there is a distance. If you select 3 atoms, angle will also be highlighted. If you select 4 atoms, torsion angle will be highlighted. So here is the distance and here it is. The units of this bond length is angstrom. So the bond length is 1.110760 angstrom. I will go to my file and in methane column I can write CH bond length is 1.11. Right. So all the bond lengths here are equivalent. You can just check for other one. Monitor distance. So it is same, right? So this way you can note down the bond length. There is no CC bond, only CH bond, so I have mentioned the bond length. Now if I want to capture the image, I will go to File, Export, select the file format as JPEG, methane, and save. Alright, let's check in our folder, Test Argus. This folder is on my desktop. I can see here image which is methane. Here it is. I can crop it or make the adjustments. Save a copy. Methane 1 desktop Test Argus. So this image is saved. I can simply copy this image, Control C, and paste it in my table. Okay, I can again picture format. I'll do it later. Let's finish with the calculation first. I will just make it small so that it is visible. Right, so here is my image of methane and its model. Next thing is heat of formation. Where will you get the heat of formation? Once the geometry is converged using quantum mechanical method, you can either go to edit and the last option is latest output file. Otherwise you can simply click over here. Here is one icon, this one, right? This is also output file for the latest molecule. Remember, output files in Argus lab are not automatically saved. They will be replaced once you run the new calculation, so you are supposed to save it if you want. Just I will scroll down and see where is my heat of formation mentioned in this sheet. So here is the heat of formation in kilocal per mole. I will just copy this value, Control C, and paste in my file. That's it. We are done with the first molecule. And there is no need to save the file. Otherwise, you can just go to File and save, save as methane text file. Saved. I will give some other name to this file, methane 1. Okay, save. That's it. Now I need to do similar calculation for ethane also. I have two options. Either I will make changes to this molecule and convert it to ethane and run similar calculations. I will suggest you not to do this. You simply can cancel this and or open new file. If I am opening new file from here, a new blank window is appeared, but it doesn't mean methane file is closed. It is still there. And remember, if you open many files at a time, your system will hang. So if you want to see how many files are open, you can go to Window, Tiles. All the windows will be shown here, how many are open. Here is the methane and the second one is for ethane. Okay, let's do. I will draw one ethane. Alright, right click, bond should be on, and right click. Two carbons with sp3 hybridization tetrahedral structure. Add hydrogens to it. It is ethane. Selection tool. This is ethane molecule. I can label all atoms and then clean geometry. So it is converged using method. Now I will run calculation, quantum mechanical methods for better results, EM1, and then start. Again, optimization is converged. So you can compare these two geometries. See, both are present on the screen. I will bring this ethane at the center. I need to monitor this C1 bond between C1 and C2. Sorry, C1 and control C2. Right? Monitor distance. Distance is 1.50 angstrom. Mark it here. CC bond length 1.50. What about CH? Let's select this hydrogen, this carbon, and again monitor distance. So it is 1.1159. I can also round it off 1.11, 1.11, let's say 2. Okay, 59. You can mention in more till more decimal places. I need to monitor angle also, although it is not asked. I will tell you. One, see, if you want to see this angle between H4, C1 and C2, you are supposed to select the atoms in that sequence only. So this hydrogen, control this carbon, and this carbon atom. So when you go to monitor, angle is highlighted now and the angle is 110.70. Although it was not asked in our aim, but still you can note it down. Another thing is dihedral angle. Dihedral angle is between the carbon atoms which are attached to adjacent carbon atoms, like the between the bonds between. Okay, I tell you, C1 and C2 are connected. H4 and H8 are the hydrogen atoms which are connected to the adjacent carbon atom. So the angle between the bond of C1H4 and C2H8 is called dihedral angle. I will select any 4 atoms. These 4 atoms, 2, 1, 2, 3, and 4. Go to monitor. Now torsion is highlighted. Torsion angle or dihedral angle are the same thing. So the angle between these is 180 degree. These bonds are completely opposite. So we have monitored bond length, CC bond length, CH bond length, and the angle between H, C1, C2, and the dihedral angle. You can monitor one more, bond angle, and this hydrogen. Monitor angle. So this angle is also mentioned. Zoom it out. You can see here 108.22. So this way you can monitor different values. You can capture this image also. File, export image, ethane, change it to JPG, and save. Open the file. Ethane is here. Control C and paste in your file. Control V. You can make adjustments. You can crop the image. So we are not focusing on that. Our aim is to calculate all these parameters. And now heat of formation. You can see output file from this icon and scroll down, or you can simply control F, heat of formation, heat. So here is the heat of formation, minus 16.75. Control C, paste it in your file over here, Control V. So this way you can perform the calculations using quantum mechanical methods. So we are done for the day. We will do some another exercise in next video. Thank you.